Hi, I'm Max Hopkins, and I'll be talking about reliable active learning with comparison queries based on joint work with Daniel Kane, Shachar, Lovett, and Gaurav Mahajan. Let's start with a background overview of the passive versus active learning paradigms. So what is passive learning? Well, we'll start with an instance space X that's some set like R to the D, and a family of classifiers H functions from the instance space X to 0, 1 like half spaces. Then the general idea is that we'll have an adversary who picks a function h from this family of classifiers and picks a distribution d over the data, and then a learner who is allowed to request labeled samples from the adversary with the goal of, after having received a reasonable number of samples, outputting some classifier h prime, which approximates the true function h chosen by the adversary in some way. What's the difference in active learning or pool-based active learning? Well, the main difference is that instead of sending one by one labeled samples, the adversary will start by sending a big pool of unlabeled data to the learner. And then the learner will additionally have access to a labeling oracle and can adaptively choose what data to send to the oracle to get labels. The idea here is that if you're in a use case where labeled data is very expensive, but unlabeled data abounds, like maybe pictures on the internet, you might be able to, by adaptively choosing what data to label, to use exponentially fewer labeled samples. We're going to add two slight modifications to this, which is that our oracle is meant to model a human expert. And unfortunately, humans make mistakes, which means we're going to want our oracle to be noisy in some manner. And second, when in the real world, we often expect that our data isn't so adversarial. And so to model this, we're going to restrict the distribution that the adversary can choose from to be something nice, like maybe it has to pick from Gaussians or log concave distributions. So I haven't told you yet what it means for this output h prime of the learner to approximate the true function h. And this has to do with what your learning model is. So the most standard, most basic learning model is probably approximately correct learning, PAC learning. And the idea is very simple. We'd like to output a classifier h prime such that with probability 1 minus delta, we learn a 1 minus epsilon fraction of the points correctly. And of course, this is very, very widely studied, and it's well known what this looks like for half spaces. We know that in d dimensions, it takes about d over epsilon labeled samples passively to PAC learn half spaces. And we also know that this is, in one dimension, this is an area where active learning truly shines, because we know that it actually only takes about log 1 over epsilon versus 1 over epsilon labeled samples. So we see this exponential gap between the passive and active learning paradigms that we were hoping for. So one thing that people have been looking into more recently in the learning community is the fact that PAC learning has somewhat weak guarantees. And what do I mean by this? Well, I'll give one example. PAC learning has a very poor point-wise guarantee. It may be that if you pick one point in the instance space and you have a PAC learning algorithm and you look at running it across all possible random seeds, it may actually mislabel this point 100% of the time. So PAC learning has no point-wise guarantee. So a lot of different methods of kind of robustifying PAC learning have been considered recently. We'll consider a somewhat old one, which is that we're going to allow the learner to respond, I don't know, in cases where it isn't confident, instead of forcing it to guess. This was introduced in the late 80s by Revest and Sloan under the name Reliable and Probably Useful Learning, and it's been reintroduced under a number of different names in the last decade, but we'll focus on this initial learning theoretic framework from Revest and Sloan. So what is RPU learning? Well, the idea is that we want to output a classifier h prime which satisfies two properties. It has to be useful, which means with probability 1 minus delta, it shouldn't say I don't know very often, less than an epsilon fraction of the time. And second, it should be reliable, which means when it does label a point, it must be correct. So an RPU learner cannot make errors. This raises a very natural question. In the real world, is RPU learning feasible? And the answer, unfortunately, we already know is no. And why is this the case? Well, RPU learning can't tolerate noise at all because it has to be perfect. And it's also, even in the noiseless case, it turns out for simple concept classes like rectangles or half spaces, it's not computationally feasible. It's computationally intractable. And so in this work, we introduce somewhat of a more feasible model, a mixture between PAC and RPU learning that we call almost reliable and probably useful learning, ARPU learning. So what is this? Well, our goal, it's very similar. Our goal is to output a classifier h prime, which with probability 1 minus delta satisfies these two properties. It's useful, so it doesn't say I don't know very much, and it's reliable. When it does label a point, it does so correctly. So what's the difference? The difference is that in ARPU learning, a delta fraction of the time, there's no guarantee on what the learner does. It could get everything wrong. It could say I don't know as much as it wants. So why would you care about a learning model like this? versus pack learning, well, ARPU learning actually comes with some very nice point-wise guarantee, where if you fix a point and you look across all runs of some ARPU learning algorithm, the learner can only get that point wrong a delta fraction of the time, versus in pack learning where it could actually be wrong every time you run the algorithm. Okay, so now that we've covered kind of these learning models and background, let's take a step back and let's look at kind of what is the overarching goal of active learning? What's the gold standard for an active learning algorithm? Well, we'd like it to satisfy these 4 properties. First, we'd like it to be query efficient, which is kind of regardless of model. We'd like it to take about polylog 1 over epsilon queries. We'd like it to be computationally or time efficient, meaning it should take only time poly 1 over epsilon. We'd like it to be noise tolerant in some manner. And as a bonus, we'll kind of throw in this 4th thing that's maybe considered less in the active learning literature, but we'd like it to be robust or reliable in some way beyond the standard pack bounds. Okay, so let's jump into our results. And what's the first thing to look at? Well, it's reasonable to ask, for simple concept classes like half spaces, is achieving the gold standard possible? And unfortunately, the answer is no. And we've actually known this for quite a long time. Back in 2005, this group proved that you couldn't query efficiently pack learn half spaces in 2+ dimensions. And this is even true under nice distributions like a unit ball. And so here's some even worse news. Far from being just not query efficient, it turns out that ARPU learning is just flat out impossible. And why is this? Well, let's consider this example that's actually very similar to Dasgupta's initial 2005 lower bound, which is we'll take a circle and we'll take an adversary who picks kind of randomly a tangent hyperplane to the circle. And so they're picking one point to be labeled as red and the rest of the circle to be labeled as blue. And now consider a learner here who only queries a finite number of points. Well, first of all, they've only learned a 0 probability mass of the circle. They've only learned these, finite points that they've queried. And second of all, with probability 1, they have not found the red point, which means to learn some reasonable fraction of the circle, they're just going to have to guess. And if they guess, then a constant fraction of the time, they're going to mislabel the red point, but that's not allowed in ARPU learning. So how are we going to get past these 2 problems, right? It seems like, okay, half spaces, we can't learn them query efficiently, we can't learn them reliably. How are we going to get around this problem? Well, we're going to adopt an idea that's been gaining traction recently in the learning community, which is to ask better questions, to ask more informative questions. The idea here is that if we're modeling our oracle as a human expert, why are we restricting ourselves to just sending it a single point and asking, what is the label of this point? Why aren't we sending it multiple points and asking more interesting questions about the data, more informative questions? And so one very simple type of question like this is a comparison query. And this is like sending your oracle 2 pieces of data. Say your oracle is a doctor and you're sending them 2 MRI scans. And you ask the doctor, which of these patients do you think is sicker? More formally, you maybe ask the oracle, which point is further away from the decision boundary? And it turns out we already know that comparison queries come with fairly significant added theoretical power. So a couple of years ago, it was proved that comparisons can make pack learning time efficient in the Tsibikov noise model, which is a fairly strong noise model where usually we can't get time efficiency. And just last year, we proved that comparisons actually make, in a noiseless setting, make RPU learning efficient, only logarithmically more expensive than pack learning. And so it's worth noting that this isn't just some theoretical thing we've pulled out of the void. Comparison queries have been used in practice for decades, both in recommender systems and in ranking systems. Okay, so now that we've covered kind of enough background about what our model is, we can give the 20,000-foot view of our work, which in a sentence is that comparison queries achieve the gold standard. What do I mean by that? I mean that there exists an algorithm using comparisons, which is 1, query efficient, 2, computationally efficient, 3, noise tolerant, and 4, reliable. Let's take a closer look. So the first model we'll look at is Massart or bounded noise. And this just means that the oracle can err with probability up to some parameter eta. And our theorem says that there exists some algorithm which reliably learns half spaces in d dimensions under restricted to S concave distributions, where the oracle is allowed to err with probability up to 1/2 minus lambda. And it has the following properties. It's time efficient, it doesn't use too many unlabeled samples, and it's query efficient. It only uses about polylog 1 over epsilon queries. And there's a caveat here, which is that the time efficiency is exponential in this parameter lambda, and we'll talk a little bit later about where that comes from. It's worth noting that this theorem actually holds for more general concept classes rather than just half spaces. It holds for anything with finite inference dimension, which is a complexity parameter we'll talk about later, and in a distribution-dependent setting under average inference dimension. Okay, so how does this compare to previous work? Well, previous work focused entirely on half spaces that went through the origin. This is previous work on query efficient algorithms. because they couldn't beat Dasgupta's 2005 lower bound for non-homogeneous half spaces not going through the origin, if they didn't use comparisons. So basically, these works went along two axes, time and distribution. And basically the idea was that they became more and more time efficient, and they worked over a wider range of distributions until we hit this 2017 work from Balkan and Zhang that was time efficient and worked over isotropic S-concave distributions. So what do? Well, we drop the isotropy condition. We work only on S-concave distributions, and we add reliability. We generalize to the full set of half spaces, not just ones passing through the origin, and we remain time efficient. Okay, so the second model we look at is something that we call simplified Sivakov noise, and the idea here is just that the boundedness of Massart noise is a little unrealistic. And as you approach the decision boundary, as you approach the break between plus and minus, you would expect that the noise rate in your label would go to 1/2. And similarly, this is easily extended to comparisons. As you hand a doctor kind of two images that look arbitrarily similar, you would expect the error rate on comparisons to go to about 1/2. So this is a much harder model, and we know that there are query lower bounds of poly 1 over epsilon, both just for labels and prior work, and we proved this for comparisons in our work. So what's the theorem say? Well, it basically just says that there exists an algorithm which reliably learns half bases in d dimensions under S-concave distributions with Sivakov noise, and it has the following properties. It doesn't use too many unlabeled samples, and it's fairly query efficient. Unfortunately, we don't know how to do this yet in a time-efficient manner. So what's the relation to prior work? Well, in 2015, Haneke and Yang proved this distribution independent method for learning general half spaces, non-homogeneous half spaces, but it wasn't reliable and it wasn't time efficient. A few years later, there was a group that proved that if you actually added in comparison queries, you could get time efficiency for homogeneous half spaces. And our work is somehow a mix. It works over S-concave distributions. It's reliable. It does work for general half spaces, but it's not time efficient. Okay, so let's talk a bit about our methods. What do these algorithms actually look like? Well, we use a method called inference-based learning, a paradigm called inference-based learning, and this is basically just CAL for enriched queries. If you don't know what CAL is, that's fine. So this algorithm is actually very simple. The idea is that we'll draw a small subset from the distribution, and we'll send it to the oracle to get labels and comparisons for all the points. We'll use these responses to build a linear program that we call the inference linear program. And this program basically just looks at any point in the inference space, and it says, based on our query responses, do we know that this point must be positive? Do we know that it must be negative? Or have we not inferred anything about it? The idea is that we then restrict the points that the LP does not infer. We should restrict the points that we didn't learn, and we repeat this process. So how long does this take? How many queries does it take? Well, to analyze this, what we need to do is we need to bound the coverage of the LP. We need to bound how likely it is that the LP actually does infer whether a point is positive or negative. And in 2017, Kane, Lovett, Mahajan, and Zhang introduced a complexity parameter called Inference Dimension that exactly bounds this quantity. The idea is that if you're working over a class like half spaces in R2 that have finite inference dimension, then they prove that you can draw a small subsample and that the LP for this small subsample will have constant coverage with constant probability. And so the idea is that if you have this guarantee, you only need to repeat this a logarithmic number of times to successfully active learn. This was extended to higher, half spaces and higher distributions by adding weak concentration and anti-concentration requirements on the distribution. The idea just being if the distribution is at least reasonably nice, when you draw a finite sample, it should have reasonably small inference dimension. Okay, so what have we actually added here? Well, in the noisy case, it turns out that this type of logical inference learning totally fails in the presence of noise, just like how CAL has to be seriously modified to get to robust CAL. So what's the idea? Well, instead of drawing a small sample and just sending it to the oracle and using the oracle's noisy responses, we'll instead draw a bunch of additional helper points, and we'll use comparisons between these helper points to build statistics to give us reliable comparisons and labels. So what does this really look like? Well, really, it's like a noisy sorting process. We'll draw a bunch of points, and we'll sort them with persistent noisy comparison errors into some sort of like maximum likelihood order. And Braverman and Mussel back in 2008 proved a very useful guarantee about an order like this. They proved that no point in the order moves too far from its original position. And so this means that if we take a big set and order them with noisy comparisons, we can use points that are fairly far separated in this order to build a reliable set of comparisons and labels. And we can then just plug this back into the linear program and use the non-noisy version to get our active learning. A big problem with this, though, is that it's not very efficient. This type of MLE sorting takes exponential time in the noise parameter, and that's where this exponential dependence in our Massart theorem comes from. Okay, so finally, we can't use this type of noisy sorting directly for Sivakov noise because it has unbounded error. So instead, we use a structure versus randomness paradigm where we say the points are either in two cases. Either they're kind of separated and structured, and then we can massage the old technique to work. Or the points are literally geometrically clustered together, and then they look random. And in fact, we can tell between these two cases by measuring randomness in comparisons. And if the points are clustered, we can use that geometric information about the cluster to infer points in the cluster. Okay, so that was a lot of technical information very quickly. What's the main takeaway? Well, you should see that comparison queries are a simple, practical method to make active learning query efficient, noise tolerant, reliable, and in places computationally efficient where otherwise it couldn't be. Thanks for watching.